All right, so today's homework involves a lot of problems that deal with exponential functions, and we kind of ran out of time before we got to go through a good set of those. So I'm just going to take about 10 minutes to record a video, have you take a look at a couple problems involving exponential functions and see if I can't make your workload a little bit easier tonight. Just for quick reference, let's talk about derivatives first. If I want the derivative of e to the sine of x, that's really taking the derivative of e to the u, which turns out to be e to the u times u prime. So here we would have e to the sine of x multiplied by cosine of x. Now, if I'm taking the derivative of 4 to the tangent of x, that's really the derivative of a to the u, which turns out to be a to the u times u prime times the natural log of a. So here we would end up with 4 raised to the tangent of x. U prime in this case would be secant squared of x, and the natural log of a would turn out to be the natural log of 4. Okay, and I bring that up because we're going to find that these constants floating around in exponential functions tend to create headaches for us that we're going to have to cancel out or deal with. One thing to note as you do your problems today, in an exponential function, if you're trying to integrate, always let u be the exponent. That'll happen 100% of the time. So a couple rules we want to consider. If the derivative of a to the u is a to the u prime ln a, then the antiderivative of a to the u prime ln a turns out to be a to the u. And an alternative version of that rule is sitting here below it. This is what happens if you don't have that ln a in place. A little typo there. All right, so let's take a look at a couple of examples. Here I have an exponential function, and in an exponential function, I'm always going to let u be that exponent. So u in this case is going to be negative x cubed. So in the rewriting process, this is going to become e to the u. If I plug the 2 in to my new u function, that upper limit will become negative 8. If I plug the 0 in, that lower limit stays 0. Now, let's go to work on what's left to be replaced. X squared dx. Quick note here, the derivative of u with respect to x is negative 3x squared. Therefore, du turns out to be negative 3x squared dx. Now, my goal is to replace x squared dx, so I'm going to divide the negative 3 out of both sides of this, and I'll be left with du is du over negative 3 replaces x squared dx. So I'll set the negative 3, or negative 1/3 constant to the front, and du here. Well, the antiderivative of e to the u times du turns out to equal e to the u. We're going to do that from negative 8 back to 0, and that's going to leave us negative 1/3 times e to the negative 8 minus e to the 0. Of course, e to the 0 would equal 1. All right, a little tougher scenario is when I'm dealing with a base other than e. Again, I'm simply going to let the exponent represent u. So u in this case is going to be x squared. Therefore, u of the square root of 2 is going to be 2, and u of 1 is going to be 1. So a quick rewrite of this integral is going to give me 2 to the u from 1 to 2, and all of this has been replaced. But now I need to replace the x dx. Well, du dx is 2x. So du is the same as 2x dx. I'm trying to replace 1x dx, so we divide both sides of this by 2, and we're left with du over 2 is equal to x dx. So we'll put the 1/2 here and the du here. Now the problem is I'm missing something. When I see this problem, what I really wish is that there had also been an ln2 in here, because then I've got my a to the u, here's part of the u prime, and here's that ln a. Well, since this is a constant multiple, I can put it there as long as I put a 1 over ln 2 up here. So I put the ln 2 on the inside of the integral and 1 over ln 2 on the outside. Now I'm ready to go to work. So we'll go with 1 over 2 ln 2. The antiderivative of a to the u prime ln a turns out to be a to the u. That's going to be from 2 to 1, which is going to leave me with 1 over 2 ln 2. 2 squared is 4. 2 to the first is 2. I'm going to end up with 2 over 2 ln 2, or finally 1 over the natural log of 2. All right, let's look at one more example. Again, the first thing I note when I see this problem is, oh, I wish there had been an ln 2 here. I've got an a to the u, I've got a u prime, sort of, but I don't have an ln 2 because it's a constant. I'm just going to put it there. ln 2 on the inside, 1 over ln 2 on the outside, and that's going to clear up a bunch of my headaches. U is going to be the cosine of x. So u at pi over 2 would be the cosine of pi over 2. 0. U at 0 would be the cosine of 0, and that's going to be 1. So the 1 over ln 2 constant multiple that I put in is coming with. The new limits are going to be 1 on the bottom, 0 on the top. 2 cosine becomes 2 to the u, and now I'm still going to have to replace this thing. The derivative of u with respect to x is negative sine of x. So du is negative sine of x dx. Therefore, negative du is going to replace sine of x dx. We'll go negative out front and du. Keeping in mind, I've still got this ln 2 that I added on the inside of the integral. So I've got it in the form a to the u prime, and ln a, easily integrable. So the negative 1 over ln 2 comes with. The antiderivative of a to the u prime ln a is simply a to the u, and it will go from 0 to 1. So I end up with negative 1 over ln 2. 2 to the 0 is 1. 2 to the first is 2. End up with a double negative as my numerator, and we go with 1 over